Oh, good morning, everyone. Thank you for organizing this workshop. And yeah, be free to make questions during the talk. It's a very informal workshop, so please do it. I am Olga Muñoz. I am the head of the Cosmic Dust Laboratory that is located at the Instituto de Astrofísica Andalucía in Granada. The IAA belongs to the Spanish Research Council. I'm going to talk about optical properties of Martian dust. One is behind the screen that is focused on laboratory measurements. And Julia, after the coffee break, will talk about the modeling part. And indeed, you will see some slides repeated here in her talk, because yeah, we think that the only way of improving our models or our idea of how this dust affect the relative balance of the atmosphere is by combining laboratory data and modeling. So, okay. Let's move. Okay, thank you. I thought I have to point to the computer. So this is the outline of the talk. I will give a very brief introduction on the roadmap, because roadmap, the project is focused on studying the role of dust and clouds on the Martian atmosphere. So it says, yeah, I will give just a very brief summary on the goals of this project. And this is a workshop. I will start giving some definitions that can be useful for understanding the other part of the talk, and maybe some other talks during the workshop. In that context, I will explain why we need experiments, how we can get information from experiments, and how can we use those experimental data. I will present the experiments we have at the Cosmic Dust Laboratory, the experiments and the samples, how we can produce those samples and the characteristic of those samples, and of course, some results. When I was thinking of giving a brief introduction of the project, I just remembered that we have a very nice animations in the roadmap website. You can have a look. Where's the pointer? You can have a look at there. And the first animation is a very nice introduction on the project. So let's see if it works. So yeah, in roadmap, we combine laboratory data from different laboratories in Granada, Madrid, Duisburg, and Aarhus, with simulations and data from space missions, in particular from the instrument SPCAM on board Mars Express and NOMAD on board ExoMars. And the main goal is to better understand the role and impact of dust and clouds on the Martian atmosphere. Well, we all know that Mars is covered by dust, and this dust is lifted into the atmosphere, producing hazes and clouds. And well, this storm can be local or global, and they also have different time scales from hour to seasons. This cloud of particles interacts with the solar radiation. Part of the solar radiation can be reflected back into space. Part of it can be absorbed by these particles, and they also interact with the radiation coming from the surface. So the effect of these particles, thus cloud in the atmosphere, it affects the temperature profile, it affects the radiative balance of the atmosphere, and it also affects the atmospheric dynamic. So it has a very strong effect on many phenomena on the atmosphere. And if we want to properly interpret the role of those particles in the atmosphere, we have to know their physical properties, because what physical properties, particle size, shape, and composition, because depending on those physical properties, we will have different optical properties and different effect. So this is an animation from the TESS instrument during the 2001 global dust storm, where we can see how the temperature increases. Red colors are higher temperature, blue colors are lower temperatures. This temperature increases as the dust load in the atmosphere increases. So we can see that it has a very, very strong effect on this temperature profile. And also, as it is mentioned in the animation, there are many hints, if we look at the Martian atmosphere, that proves that in the past, Mars was more similar to our Earth. And it has a large amount of liquid water that produce these canyons and dry rivers. And the question is where and how this water has gone. We have seen in the animation that dust particles also have an effect on the water escape from the atmosphere. So the water vapor that is usually close to the surface is lifted with these dust particles, and then when they are higher in the atmosphere, they can be easily broken down in oxygen and hydrogen, and they can more easily escape from the atmosphere. So if we want to understand what happened with water on Mars, all these answers are linked to the composition and dynamics of the atmosphere. So this is the idea of the roadmap project. Dust particles have a lot of impact on the atmosphere. And I'm going to start now with some definitions. Some of them, maybe you probably know them, but just in case, our main tool is the electromagnetic light scattering. So when we have a single particle and it's illuminated by a light beam, it suffers from three different phenomena. It can be partially absorbed, it can be scattered in all directions, and it can also emit thermal emission at different wavelengths. That is if we have one single particle, but if we have a cloud of particles, each particle is excited by the incoming radiation and also by the secondary fields produced by the neighbor particles. However, if the number of particles in the cloud is low enough and the distance in between particles is large enough, we can assume the so-called single scattering approximation. And then the total field can be computed by just the sum of the single fields produced by each particle. This is a single case, but if we have a dense cloud of particles, as is the case when we have a global dust storm, then the problem is more complicated. We have to solve the radiative transfer equation. As we probably know, if we want to fully describe a beam of light, it can be done by this intensity vector, where I is a measure of the intensity, the scattering flux. Q and U is a measure of the degree of linear polarization, and V is a measure of the circular polarization. So this vectorial equation gives us the change in the intensity vector along the direction of the propagation of the light. In this, we have again three different components of this equation. The first one is absorption, scattering, and thermal emission. This scattering is defined by the scattering matrix. Now we have the definition for the scattering matrix. The scattering matrix of a cloud of particles is characteristic of this cloud. It does not depend on the incident or scattered radiation. And it gives us how the intensity vector or Stokes vector of the incident light is transformed into the Stokes vector of the scattered light as a function of the scattering angle. This scattering angle is defined by the directions of the incident and scattering beam. Well, it's a matrix. It seems to be complicated, but it's not complicated. This first element of the scattering matrix is just the phase function that we are all using in our models. The minus F12 over F11 element is the degree of linear polarization, and this F22 element is related to the depolarization ratio that we measure with LiDARs. What is very important is that the elements of the scattering matrix are directly dependent on the physical characteristic of the scattering particles, particle shape, particle size, composition through the refractive index, and wavelength of the incident light. Another approximation that is widely used in models is neglecting polarization. So instead of taking into account the intensity vector, we only take into account the first element, which is the scattered flux. In this case, the equation is easier. And instead of the scattering matrix in this scattering part, we only have the first element, which is the phase function. And this is the last definition. When we are talking about light scattering, particle size matters, but what really matters is the size parameter, which is the size relative to the wavelength. You remember the scattering matrix depends on particle size and wavelength of the incident radiation. Indeed, the scattering pattern depends on this quantity, which is the size parameter, that is the relative size to the incident radiation. And what does it mean is that if we have a 2 micron size particle observed in the visible wavelength, in this case in the green light, it will produce the same scattering pattern as a millimeter size particle at a radio wavelength, because they both have the same size parameter. So they will be exactly completely equivalent as far as the scattering is concerned if they have the same refractive index. And attending to this particle size parameter, we can talk about 3 different size regimes. Scattering size regimes, which is Rayleigh, when we have particles much smaller than the wavelength of the incident light. In visible wavelengths, that means the gas in the atmosphere. The resonance or Mie regime, I am not fan of this definition of Mie regime. We used to the resonance region, that is when with particle size is of the order of the wavelength of the incident light, and the geometric optics domain when we have particles much larger than the wavelength of the incident light. We will focus on measurements, on experiments on these 2 size regimes. So if we want to really take into account the role of this cloud of particles in the atmosphere, we have to somehow retrieve or measure or whatever the spectral optical thickness, a spectral single scattering albedo, spectral phase function, or a scattering function if we are not neglecting polarization, and the chemical composition. And all those parameters are dependent on particles size distribution and refractive index. The problem is that we want to compute those optical properties. We start running into problems because these are the type of particles we are talking about. This is a scanning electronic microscope image of a Martian dust analog. They present very complicated shapes. They are usually in a cloud. You have different compositions. It is a mixture. In natural dust, you have a mixture of compositions, and they are usually distributed over broad size distributions. All these make computations very difficult, if possible at all. So imagine simulating the interaction of the electromagnetic radiation with each of these particles and combining all these computations. So what we used to do is to use simplified model particles, like spheres, that is the most popular model, or more complicated shapes like spheroids, cylinders, hexahedrals. We will see more details in Julia's talk. The ME model is the most popular one because it's very easy to use. All these models are open source, so you can download it and use them for your computations. The ME model is very easy to use, and it has no restrictions about the particle size or composition that you can compute with this model. If you want to use more sophisticated model particles, then you have a T-matrix for spheroids or ellipsoids, all these particles that have a plane of symmetry. If you want to use more complicated shapes, you can also use DDA, or if you want in the geometric optics domain, you can use these Gaussian random shapes. But the problem is that you always have restrictions about the particle size or compositions that you can compute. This is the reason why we need the laboratory data, because in the lab, we can work with natural samples. So the advantage of laboratory work is that we work with well-characterized samples, which means that when we can touch the sample, we can take it to the microscope and take images. We have another device for measuring the size distribution. We can also make X-ray diffractometry to get the composition of the sample, and then you have all physical parameters of the sample, and then you can measure this scattering pattern and relate how these physical properties scatter light in all directions. The drawbacks of the laboratory data is that, of course, we have some technical limitations. In only one laboratory, we cannot measure all possible optical properties. We cannot measure an infinite number of samples, and we cannot perform measurements at all wavelengths that we have observations from remote sensing or rovers in Mars. So the ideal scenario is to combine laboratory data with models for having a step forward in evaluating the role of dust particles in the atmosphere. So I'm going to start now describing what our laboratory. This is how we produce the dust cloud. It's produced by an aerosol generator. And we use this laser to illuminate the dust sample. So yeah, we use laser as a light source. In this case, we are using two lasers in blue and red light. And this incident light is scattered by the cloud of randomly oriented particles located in this jet stream. This is the interaction. The red spot is the interaction of the laser with the sample. And the scattered light is detected by this photomultiplier tube that moves from positions close to forward direction up to backward direction. What we measure in the lab is the full scattering matrix as a function of the scattering angle. Again, this F11 element is the phase function, this is the degree of linear polarization, and this is related to the degree of linear depolarization that we measure with LiDARs. So the scattering experiment was fully developed at the IAA, but we also have some commercial devices, as this spectrometer that can measure the diffuse reflectance spectra of dust mimicking a regolith. So we put the sample on a holder, and it is illuminated, and we measure the diffuse reflectance spectra in this wavelength range. So we have two sets of experimental data that are feeding the roadmap project. The first one is the scattering matrices at two different wavelengths. These scattering matrices can be directly used as input of the radiative models, or to test the validity of numerical techniques. As I said before, we can use simplified model particles to compute the scattering pattern of dust particles. We can use spheroids or cylinders or whatever, but then we have to test those models with the real scattering pattern of real dust particles. So those experimental data can be used for testing the models. And the second set of data, the reflectance spectra, can be used for the retrieval of the refractive indices in this wavelength range. And Julia will tell us how to do that. So we have the experiments, and now we need the samples. We are focused on studying Martian dust. So we have chosen these 3 Martian dust analogs based on some references from different authors. But the idea is to choose a wide range of spectral and compositional variability so that they will be representative for the whole planet. It is not possible because it's a huge planet. And of course, we cannot take all possible compositions that we have on Mars, but at least we have a broad range of values. This is the JSC Mars 1, Mojave Martian Simulant 2, MMS2, that has been chemically enriched with the iron to aluminum content, and the Martian Global Simulant. And we can see that in the visible, they have a different colors. It's difficult to see in this screen, but in reality, this is it has a very bright red color. We have the samples. We ordered the samples to different companies, but they are bulk material, so they are collected from the ground. Or in the case of the Martian Global Simulant, it was artificially produced by combining different components. So what we have at the beginning is a very broad size distribution. So we have millimeter size particles, micron size, and so on. But for our experiment, we need narrow size distributions. In the case of the scattering experiments, we want to mimic dust in Martian atmosphere. And these dust particles are very small. They are lifted from the surface, and they have to remain in the atmosphere for long periods so that they can affect the radiative balance. So based on previous work, we estimate the particle size in Martian atmosphere from around 1.4 to 1.7 micrometers. In the case of global dust storm, they are a bit larger, to 3 to 7 micrometers. And some other papers also indicate that we could also have bimodal size distributions. So we cannot really work with such a broad size distribution, or we shouldn't work with this size distribution. In the case of the reflectance spectra, the reflectance spectra is only dependent on the composition of the samples. So all these features are directly dependent on the composition. It's not dependent on particle size. When we have smaller particles, the whole spectra will be brighter. If we have larger particles, it will be darker. However, we need narrow size distributions for modeling purposes, because this is a slide that Julia will use, and she will explain it much better. But the idea is that in the model, she's mimicking the regolith. So she's computing the scattering pattern of each single particle, and this scattering pattern is combined with a radiative transfer code. So for modeling, it's much easier if we have a narrow size distribution, because you only have to compute this narrow size distribution. Apart from that, this radiative transfer code only works in the geometric optics domain, which means particles much larger than the wavelength of the incident light. So for modeling purposes, we also need narrow size distributions for measuring the reflectance spectra, so that we can make Julia's life easier. And now, this is the work of our colleagues at the Institute of Ceramic and Glass in Madrid. I think they are somewhere in the. So they have done a beautiful work. If you have any questions, I'm sure they can answer them. They use a very, very long and detailed process for producing very narrow size distributions out of the bulk samples. They have milling sieving, centrifugation, decantation, and this takes really a very long time, because in every single step, they have to test that the new size fraction that they have produced, they have exactly the same composition as the bulk material, because, for instance, if during the milling, you can be selecting some you can also make some compositional selection. So in every single step, they take the sample to the X-ray diffractometer to check that the spectra is exactly the same, no matter the milling or the sieving process. And they also have to check the size distribution of every single step in the sample production. And after all this work, they can produce beautiful narrow size distributions, as I will show later. These are the samples that they have produced for the reflectance spectra experiment. These are the images. These scanning electronic images are very important, because usually the main problem that we have for producing narrow size distributions is that small particles stuck on the surface of the large particles, but they have been extremely successful in removing those particles thanks to this centrifugation and decantation process. This is the measured size distribution, projected surface area as a function of radio in a logarithmic scale. And they have produced really beautiful narrow size distributions and nearly exactly the same size distribution for the 3 Martian analogs. And these are the measurements for the Martian analogs from the 200 nanometers up to 2000 nanometers reflectance spectra. We see that they are quite flat in this region in the infrared. The Mars MMS2 sample is much brighter than the others, and they all have much stronger absorption when they get into the visible and UV. So this is the first set of experimental data, reflectance spectra. And they also produce these narrow size distributions for the scattering experiment. In this case, we have 3 different size distributions for each Martian analog. The so-called large sample, sample L, with R effective around 16 micrometers, narrow size distribution, a medium sample around 3 micrometers, and a small sample submicronic size. This is very interesting because in this way, since we have exactly the same composition, but different size distribution in different size regimes, this is in the small sample belongs to the transition region between Rayleigh and resonance. The medium sample belongs to the resonance regime, and the large sample belongs to the geometric optics regime. We can really compare study the size effect of those particles, those size ranges in the scattering pattern. We also have all these size distributions for the other analogs. So by comparing different measurement for different analogs, we can also study the composition effect on the measured scattering matrix elements. These are the same images. They are very nice. Everything that you put in the same is very nice. So you don't put a hair, it's beautiful. And you put this dust is also very nice. In my case, I've been working with dust samples for, I don't know, for a very long time. And these clean, large particles without any small particles stuck on the surface are really very impressive. These are the size distributions that we have measured for these samples. For the large sample, you have seen, they are very similar to each other for the medium size and for the small size. So let's see some results. These are the scattering matrix elements for the, okay, they are hidden there. So for the 3 different Martian dust analogs, for the samples consisting of larger particles, This is the phase function in a logarithmic scale as a function of the scattering angle. This behavior is typical for irregular dust. They show a strong forward peak. This strong forward peak depends on the on particle size and nearly no structure at side and back scattering angles. For the degree of linear polarization, we get a bell-shaped function with a negative branch at large scattering angles. That is not very important for Mars, but it's important for solar system applications because this negative branch has been observed in many solar system objects. And this is the F22 that is linked to the degree of linear depolarization. These are the imaginary part of the refractive index that Julia has retrieved from the reflectance spectra. So we can see that the JSC sample is in the red light is slightly more absorbing than the other two samples. And we can see that effect in the maximum of the degree of linear polarization and also in these two elements of the matrix. Okay, so we are doing the measurements at two different wavelengths. As if you remember the reflectance spectra, the samples are much more absorbing in the blue light than in the red light. And these are the measurements for the MMS2 sample. Again, the sample consisting of larger particles in the blue light, blue symbols, red light, red symbols. We do see a very strong effect of these absorption differences. The imaginary part is one order of magnitude in the blue-red that in the blue light than in the red. We do see the effect on the phase function, especially in the degree of linear polarization that presents a blue polarization color. The polarization is much higher in the blue than in the red. And in general, we see that effect in all elements of the scattering matrix. We also, since we have these three size ranges, we can also study what is the size effect in the scattering pattern. In this case, I present the measurements in the blue light for the L and M sample. We see the effect on the forward diffraction peak. As I have mentioned before, the forward diffraction peak, forward peak depends on particle size. The larger the particles, the narrower the forward peak. And we can see that the sample consisting of larger particles has a narrow forward peak, and the particles in the resonance domain has a wider forward peak. We do see the effect on the maximum of the degree of linear polarization when moving from the resonance domain to the geometric optics domain, the polarization, the maximum increases, and it shifted toward smaller scattering angles. And we also see that which size range is producing this negative branch that I mentioned before. Again, this is very important for Martian for cometary dust and asteroids. We can also see the effect of particle size in this element. Here I present the measurement for two different two different samples, sample L and medium. Here now in the red light, and again we can see the differences in all elements of the scattering matrix. So these measurements can be used as inputs for the radiative transfer models, but I also mentioned that they can be used for testing numerical techniques. Julia will present comparisons with very sophisticated model particles, but I will focus on these spherical particles. What if instead of taking into account these particle shapes, we assume that these particles are spherical? I have done a very simple experiment. I like experiments, so I do experiments. This is a glass sphere, and this is a kind of disco ball, also made of glass. Different size, but still they are in the geometric optics domain. They are huge, and I am using a flashlight in the visible light. Let's see if oh no, Can you click on the movie? So I am illuminating the spherical ball with the flashlight, and we can see that all the light is going in forward direction. You can see it, but it is nearly no light outside, and we'll see some light at backward direction. If we illuminate the disco ball, it makes its work. It's a disco ball. It has to scatter light in all directions, and yeah, that is what it does. So the scattering pattern of a spherical ball or a disco ball will be completely different, even if they have the same composition. We can see that in our planet, if we have water droplets, we have a rainbow. If we have a dust storm coming from the Sahara, we have a red sky. The disco ball is a very special shape, but this is the shape of Martian dust particles, so they are also very complicated. So the exercise is very simple. We have the sample. We know we take the sample to the microscope. We know the shape. We know the color. We know the size distribution. We measure it with another device, a particle sizer. And we measure the phase function, well, the whole matrix, but I will focus on the phase function because you all are more familiarized with this phase function. We have the forward peak, a strong forward peak, and no structure at side and back scattering angle. And this behavior is typical for irregular dust. So now let's assume that instead of this type of particles, we have spheres. We know the size, the refractive index of our sample. We know the size distribution. So we use this size distribution and refractive index in our ME model to see how these spherical particles will scatter light. And this is the result. This is the phase function for the same size distribution and refractive index as this Martian dust analog. The absorption is very low, and this is a typical phase function for low absorbing spherical particles. This is the rainbow that we see in the sky. So this is a typical, the spheres produce a very typical features in all elements of the scattering matrix. But now imagine that our instrument in our space mission or our rover is measuring the phase function of Martian dust. We have the phase function. Somehow we know the size distribution, but we have no idea about the composition of the samples. So we have a phase function and a size distribution and a ME model. And we start playing with the ME model to get a good fitting to the observational data. Then we start increasing absorption, and we get this dashed line. If we keep on increasing absorption, we can finally get this shape that we measure in the lab for the Martian dust analog, because absorption brushes out all spherical scattering features. The problem is that the ME model is also producing the single scattering albedo that we will use in our models. And the original single scattering albedo, by assuming a realistic refractive index, is 0.92. But if we keep on increasing absorption, then the albedo will be much smaller, 0.54. And the impact or the effect of this cloud of particles in our model will be completely different as if we will be using a realistic model particle. If we are brave and we want to use the full scattering matrix in our models, the scenario is even worse, because the other elements of the scattering matrix are very dependent on particle shape. This is for the phase function. The degree of linear polarization has a lot. I mean, this is 10%. The maximum with the spheres is 40%. And especially this F22 over F11 is equal to 1 at all scattering angles in the case we have spherical particles. So there is a huge difference if we assume realistic dust. And for the other elements, we also get very dramatic differences as compared with realistic dust particles. So we have two sets of experimental data, scattering matrices and reflectance spectra. From the reflectance spectra, we are retrieving the refractive indices of the samples, and we want the people to use those data. So we have a database where all these experimental data refractive indices are available for the scientific community. I don't know if we can click in the this is So this is the address of the database. If we click on samples categories, we have the Martian analog section that will be fed with all these measurements. So far, we have some measurements, and by clicking on this, for instance, on the table, you will get the size distribution of our samples, so you can use them in your models. If we'll go back, especially this, the table of the measurements, you have the whole, the full scattering matrix information on the wavelength. This is the angle of the measurements at different elements of the scattering matrix and the errors. And the only condition for using the data is please cite the paper and the database, because this is the only way for getting funding for maintaining the database. And if we go back, well, the measurements are performed from 3 degrees to 177 degrees, but for right transfer models, we need the full scattering angle range. So what we also make these synthetic scattering matrices that they are extrapolated so that they are defined from 0 degrees to 180 degrees. I know extrapolation is a forbidden word, but we fix some conditions so that the extrapolated points have some physical meaning. So it's not a polynomial extrapolation without any logic in there. So I invite you to use this experimental data. I think that's it. If you have some questions, I am happy to answer if I know the answer. Hi, Luca.
Thank you. Is there a technical reason why you couldn't make measurements up to 180 degrees? This is my first question. The second question is, what are so you mentioned at the beginning that you can neglect polarization in certain cases. So what are the cases where polarization needs to be accounted for?
I have some extra slides. It will be important if your instrument is only measuring flux and you are under single scattering conditions, it's okay because you are only measuring flux. I think I can go. No, it was a hidden slide. The problem is when you are into multiple scattering, you have multiple scattering effects. Okay, go down. One more. More. Yeah, keep on going. Okay, yeah. One more. But one more. Yeah, on the 20. Yeah. The problem is when you have, I'm destroying the multiple scattering effects, because in general, in that visible light, stellar light can be assumed as unpolarized. Put it on the presentation mode. Yeah. Okay, yeah, okay, so then go back to the, so by multiplying the other one, okay. So here you have, this is starlight, it's unpolarized, this is the intensity vector. So just by multiplying the scattering matrix by the incoming light, you have this intensity vector. Our detectors can only measure intensity. we will measure, this is the phase function multiplied by some constants, so it's okay. But now, if we go to the next slide, and the multiplier scattering effect, one particle will be excited by the solar radiation. It will scatter light, and this light will be scattered, scattered by this particle. In that case, the next slide that is is here, hidden by the sun. Beautiful. In this case, we are not multiplying by the Stokes vector of the solar light anymore, because it has been scattered before. And remember, in this case, the first element of the intensity vector will be the F11 plus the F12. Even if we are only measuring flux, in this first element, we are neglecting this term. And if we have multiple interaction with multiple particles, then you keep on adding different elements only in the first element of the Stokes vector. So this is the problem. It has been evaluated, and it was, if I remember well, by Daphne Stamm and Fernando Moreno in the case of comets, and Daphne Stamm in the case of planetary atmospheres. And the errors that you can commit by neglecting polarization in the optical depth can be up to 20%. So it's really a lot. So it's worth a try. The technical problems.
The technical problems for
Okay,
not measuring up to
go to the presentation mode. Yeah. Okay. So now you can see it. Yeah, this is the intensity vector from the first interaction of the particle, and then if you multiply, you have F11 I0 plus F12. Okay, now the experiment was before. Okay, here. Yeah, the problem is that the detector has a width. So if we are exactly in forward direction, we are having together the incoming light, the laser, plus the scattered light. And then the incoming light is order of magnitude higher than the scattered light. In the case of the backward direction, if we put the detector at 180 degrees, we are blocking the laser light. If you want to measure exactly the forward direction and backward direction, there are special devices to do that, because you can always send the scattered light to another, by means of a mirror, to another position, but then you either measure forward and backward, or you measure the other scattering angle range. Both of them are very difficult.
Thank you for your talk. Just maybe a naive question, but I was wondering, in your experiment, you measure fluxes to deduce the elements of the scattering matrices. And what I don't get is that in your equation, in the Stokes vector, there are 4 elements, so that gives you 4 scalar equations. But sometimes you show 6 different elements in the matrix. So how can you calculate 6 unknown with 4 equations?
Okay. Okay. The first part is the experiment. Oh, where is it? What we measure is the scattering matrix, the elements of the scattering matrix. In general, we have in the general case we have 16 different elements. Your question is about these 0 elements, or how we measure the different elements of the matrix?
How do you measure the different elements?
Okay. In any case, these elements are 0 under some conditions of the scattering particles. If we have randomly oriented particles, to start with, we have all scattering planes are equivalent, so we only measure as a function of the scattering angle, because the azimuth dependence is not all scattering planes will be exactly the same. And if we have some mirror symmetry, that means that for each right hand, we have a left hand somehow, because our sample has many different samples, then we only have 6 independent elements of the scattering matrix. So we measure, and in any case, we measure all of them. And let's see the experiment. Okay, it's here. I have given a very brief introduction on the experiment, but here you can see that we have a modulator, a polarizer, and in the photomultiplier detector, we have also a polarized analyzer and a quarter wave plate. So we modulate the perpendicular and parallel components of the incident light. And by changing the orientation of the different optical elements in the optical train, we can get elements or combinations of elements of the scattering matrix. So for measuring the full matrix, we need to repeat 6 different combinations of optics for retrieving all these elements. We measure all elements, also those that are supposed to be 0, to check that we are really under the conditions that we are assuming randomly orientation and mirror symmetry. But yeah, we have to play with the different components in the setup.
Is it 0?
The 0 ones are 0? Yeah, very 0. Indeed. Yeah, within the error bars, they are 0. We have done we have done many tests to check that everything is properly working in the lab. One of the things we do to test the lab is to measure spherical particles. The spheres are the more difficult particles to work with, because they have a very well-defined features that has to be exactly in the same place and so on. What we have done is to simulate, because we have many optical elements in the optical path, and these non-zero elements can be related either because the sample is not as we are supposed to, it is supposed to be, but also because we have some misalignment of the optical axis of the optics. So what we have done is to simulate what if we have an offset of 1 degree, 2 degrees, 6 degrees in each of the elements of the optical train. And then when we start measuring the spherical particles, sometimes we get non-zero elements that are supposed to be 0. And then we can compare with our simulations and see, okay, what we have here is that the polarizer is not properly oriented or so on. Once we test that, we have never measured any different from 0 with our samples. We have the aerosol generator produce a turbulent flow, so it's very difficult. And we tested also if there is some alignment of the particles by tilting the nozzle of the nebulizer, and we didn't see any differences, so they are not oriented along a preferential direction or anything. We also test that we are under single scattering conditions. Or I can tell you many tests, but yeah, that is, yeah, it's obvious to think, okay, we really get 0. And sometimes if the sample is consists of a very broad size distribution, then the sample is very noisy, and sometimes you get some peaks in there, but it's at the end is you have a boulder in the aerosol bin, and then you have it's really ruling the scattering pattern. So the broader the size distribution, the more difficult the measurements, the more noise.
Are there questions online? If not, then this is perfectly timed because it's 11 on the dot. So next presentation.